Previously on the advent of cyber. Compromise has been confirmed within the Best Festival company infrastructure. However, Santa's SOC team wonders if there are methodologies that would help them perform threat detection faster by analysing the logs they collect. Elf McSkitty is aware of Sigma rules and has tasked you to learn more and experiment with threat detection rules. And then user ID, I'm just going to give it 1337. Status is going to be experimental still. Description, looks for service discovery indicator of compromise, so it has to contain both of these, and fingers crossed when we run it it says we've completed it, and then we can get the flag. Hello world and welcome to Hacks. We are back with day 19 of TryHackMe's Advent of Cyber. The title of this room is Hardware Hacking, Wiggles Go. It probably won't surprise you that I have zero to little experience with hardware hacking. I've played with Arduino devices and Raspberry Pis and things like that, but to the extent that we're going to be covering it in this room today, I have never gone that deep into hardware hacking. But as always, we must first understand where we are in the story of the nightmare before Alfmas, and we must check in with Elf McSkitty and find out what's been going on. So without further ado, I bring to you the story, Spying on Santa. Elf McSkitty was doing a regular sweep of Santa's workshop when he discovered a hardware implant. The implant has a web camera attached to a microprocessor and another chip. It seems like someone was planning something malicious. We must try to understand what this implant was trying to do. We will deal with the microprocessor and the web camera in future tasks. For now, let's try to uncover what the other chip was being used for. Have you seen the size of Elf McSkitty's pupils? Can you tell me what's going on there? That is some seriously strong coffee. So I think the best way for me to cover this room is to just go through and read it this time. There's going to be a lot of information in here that I've never come across before, so I'll read it to you and try to understand it as we go along and see how we get on. And the author of the room has advised us that the VM that we're going to be using will take about 8 minutes to spin up, so it's probably a good idea to start the machine now and just let it spin up in the background so that all the programs and everything can load. And the learning objectives of this room are as follows: how data is sent via electrical wires in low-level hardware, hardware communication protocols, how to analyze hardware communication protocols, reading USART data from logical capture. Welcome to the Matrix. Hardware hacking is often shrouded in mystery and seen as a super complex topic. While there are a lot of in-depth complex hardware hacking components, getting our feet wet is actually pretty simple. Computers today are incredibly powerful. This allows them to build additional features and safety measures into their communication protocols to ensure that messages are transmitted reliably. Think about Transmission Control Protocol, or TCP, which has multiple redundancies in place. It even sends 3 packets just to start a communication, and that will be your TCP three-way handshake, SYNAC or SYN-SYNAC. In the world of microchips, we often don't have this luxury. To make sure our communication protocols are efficient as possible, we need to keep them as simple as possible. To do that, we need to enter the world of zeros and ones, or binary. This then begs the question, how does hardware take electricity and generate signals? In this task, we will focus on digital communication. For hardware communication, we use a device called a logic analyzer to analyze the signals. This device can be connected to the actual electrical wires that are used for communication between two devices that will capture and interpret the signals being sent. In this task, we will use the logic analyzer to determine the communication between two devices in the rogue implant. The electrical heartbeat. Back to our question, if we have electricity, how can we generate a digital signal? The approach most hardware components take is to simply turn the power on and off. If the power is on, we are transmitting a digital 1. If the power is off, we are transmitting a digital 0. So the presence of an electrical pulse indicates 1, the lack of an electrical pulse indicates a 0. We call these ones and zeros bits. To perform communication, we simply turn the power on and off in a specific sequence and transmit a bunch of zeros and ones. If we send 8 bits, so whether it's on or off, we are sending a single byte. Voila, we have just performed digital hardware communications. These are wonderful squiggly lines that you would see on the logic analyzer, as you can see below. And it's the same with fiber optics as well with light. So if you're sending a light signal, it can be considered a 1. If it's dark, as in no light, then it can be considered a 0. We can transmit text data by using the ASCII table. Sending the binary representation of each character, we can transmit data. However, it isn't actually just that simple. If we wanted zero effort in our communication, we would need an electrical wire for each 0 or 1 that we wanted to transmit. Considering that a single character is 1 byte of data, thus 8 electrical wires, this can become a mess of wires really fast. To make this more efficient, we need to use fewer wires, and they have both hardware chips agree to a specific digital protocol and configuration that will be used to transmit the data. Let's look at some of the most common protocols and how they work to send data still while reducing the number of wires we need. I'm going to go with USART. Please correct me in the comments if I'm wrong. USART, Universal Synchronous Asynchronous Receiver Transmitter. USART communication, or as it is better known, serial communication, is a protocol that uses 2 wires. One wire is used to transmit TX data from device A to device B, and the other wire is used to receive RX data on device A from device B. In essence, we connect the transmit port from one device to the receiver port from the other device and vice versa. What is interesting about this protocol is that there is no clock line that synchronizes the communication of the devices. Without a clock, the devices have to agree to the configuration of communication such as the following. Communication speed, this is also called the baud rate or bit rate and dictates how fast bytes of data can be sent. Agreeing to specific rates tells each device how fast it should sample the data to get accurate communication. While there are fixed standards for baud rates, devices can choose to use any other rate as long as both devices support it. So if you've ever connected to a hardware device via PuTTY, you may know that you have to set a baud rate. Bit per transmission, this is normally set to 8 bits, which makes a byte, but it can be configured to something else such as 16 bits. Stop and start bits, since there is no clock, one device has to send a signal to the other device before it can send or end data transmission. The configuration of the start and stop bits dictate how this is done. Sounds a bit like TCP. Parity bits, since there can be errors in communication, parity bits can be used to detect and correct such errors in the transmission. Once the 2 devices agree on the configuration of the serial lines, they can now communicate with each other. A single transmission is shown in a diagram below on how ASCII character S would be transmitted. There are a couple of caveats, however. The devices don't really have a way to determine if the other device is ready for communication. To solve this, some USART connections will use 2 additional lines called clear to send (CTS) and request to send (RTS) to communicate to the other device whether it is ready to receive or ready to transmit. Furthermore, to agree upon what voltage level is a binary, 1 or 0, a third wire called the ground wire is required to allow devices to have the same voltage frequency. However, despite all of this, USART is an incredibly popular protocol in microprocessors due to its simplicity. Yeah, it sounds good, it doesn't sound like there's major problems there. SPI, the Serial Peripheral Interface Communication Protocol, is mainly used for communications between microprocessors and small peripherals such as sensors or an SD card. While USART communications has the clock built into the TX and RX lines, SPI uses a separate clock wire. Separating the clock SCK from the data DATA line allows for synchronous communications, which is faster and more reliable. So the trade-off is adding an additional wire, but we gain speed and reliability boost. An example of the same S being transmitted using SPI as shown below. So they've added an additional wire in, which allows you to sort of time things better. The clock line tells the receiving device exactly when it needs to read the data line. Two-way communication is also possible, but quite a bit more complex than serial communication. Essentially, one of the devices is labelled the controller. This is the only device that is allowed to send clock signals. All other devices become secondary devices that must follow the controller's clock signal to transmit data back. If two-way communication is used, instead of having a single data line, 2 lines are used, namely peripheral in controller out (PICO), which means communication is sent from the controller, and peripheral out controller in POCI. Geez, what's going on here? Which means communication is sent from the secondary device back to the controller. Using this, the controller sends a clock signal and a command out to the device using the PICO line, and then keeping the clock signal, the controller receives data back on the PICO line as shown in the diagram below. So I believe what that means is there's one device that controls like the clock speed and controls when data can be sent, and that uses the Pico line to communicate data. Then when the other device wants to respond, it will use the POCI line, the peripheral out controller. So they have their own sort of independent lines, but ultimately the main device controls it with like the clock speed, I think. There is also one additional change that can be made. While there can only be one controller, there can be multiple secondary devices. To save wires and ports, all devices can use the same SCK, Pico and POCI lines. A fourth wire called the Chip Select CS wire is used to distinguish the devices that communication is meant for. The controller can use that line to indicate to a specific device that it wants to communicate to it, as shown in the diagram below. Sounds a bit like a bus network. SPI communication is a fair bit more complex than USART, but having a dedicated clock line increases the speed at which we can communicate and improves reliability. Okay, we are about to get meta with the I2C, or the Integrated Circuit Communication Protocol. It was created to deal with the drawbacks of both USART and SPI communication protocols, because USART is asynchronous and has the clock built into the transmission and receive lines. Devices have to agree ahead of time on the configuration of communication. Furthermore, speeds are reduced to ensure communication remains reliable. On the other hand, while SPI is faster and more reliable, it requires more wires for communication, and every single additional peripheral requires one or more chip select wire. I2C attempts to solve these problems. Similar to USART, I2C only makes use of two lines for communication. I2C uses a serial data SDA line and a serial clock line for communication. However, instead of using a chip select wire to determine which peripheral is being communicated to, I2C uses an address signal that is sent to the SDA wire. This address tells all controllers and peripherals which device is trying to communicate and to which device it is trying to communicate to. Once the signal is sent, a data signal can be used to send the actual communication, to notify other controllers and peripherals that the communication is taking place and prevent these devices from talking over each other. A start and stop signal is used. Each device can monitor these start and stop signals to determine if the lines are busy with communication. An example of such data transmission is shown below. Since an external clock line is used, communication is still faster and more reliable than USART, and while it is slightly slower than SPI, the use of the address signal means up to 1008 devices can be connected to the same two lines and will be able to communicate. Now that we understand the basics of hardware communication protocols, we can look to analyze the logic of the rogue implant. It's not lost on me that these protocols appear to mimic network protocols. With the starting and finishing of data, you have the start and send signals, a bit like the FIN and the FINAC and SYNAC protocols of TCP. And it also makes me wonder whether in the future one protocol will come out as the supreme protocol, as the main protocol like TCP IP is today. Probing the logic. After sending this rogue implant to the forensic lab for analysis, the following circuit diagram is uncovered. Based on the diagram, it seems there is a microprocessor that is connected to an ESP32 chip, which is a real chip. It's the one that the Flipper Zero Wi-Fi developer board uses. It's a Wi-Fi chip that you can use to sort of do Wi-Fi stuff, de-auth attacks. There's a lot more to it. I'm just speaking with my experience. Doing some research, we can see that the ESP32 chip allows microprocessors to communicate over Wi-Fi and mobile networks. So whatever this implant was doing, it was definitely communicating somewhere else, or with someone else. If we can intercept the communication between the microprocessor and the ESP32 chip, we would be able to see what commands and information are being sent. It seems like the perfect opportunity for our red and blue team to team up. Alpha Forensic and Alpha Recon are on the job. The Alves realised that these chips probably use digital communications that can be intercepted with a logic analyzer. Looking at the wires between the chips, we see a black wire connected to a pin called ground, and a red wire connected to the pin called VIN. Yep. Our forensic knows from experience that this would be the ground and voltage in wires, respectively, meaning that these wires are used to provide power to the chip. That then leaves the green and purple wires that would be used for data transmission. Yep. Seeing that they are connected to the RX0 and TX0 pins, Alpha Recon can deduce that this refers to the transmit and receive lines of the USART communication communication. Hence, we are pretty sure that the protocol used for communication is USART. Armed with this information, the elves connect the probes of the logic analyzer to the green and purple wires before powering on the implant. Immediately, super fast signals are seen on the analyzer. The elves create a logic data dump from the signals, and McSkitty is asking you to investigate what is actually being transmitted. Analyzing the logic. In order to analyze the logic data dump, we will need to use a logic analyzer tool called Slayer. Start the machine attached to this task if you have not already, which will open in a browser and will have all the required tools installed for you. Once the machine is loaded on the desktop, double click the Logic 2 application. So we've spawned the machine and we're going to double click Logic and see what happens. Let's import the logic data dump. To start our analyzer, select the Open a Capture option and select Santa file from the desktop and click Open. So we're going to go here, we're going to go File, Open Capture, and then from the desktop we are going to select Santa. Once imported, you can ignore the calibration error pop-up. You should be able to see the captures. If you hold left control and use the mouse wheel to zoom out a bit, you should be able to see the digital signals. So hold left control, he said, and move. Okay, we're seeing a little something now. I'm not sure if it's what we're supposed to be seeing. D0 and D1 refer to the digital channels of the two lines that were probed. A0 and A1 refer to the analog data from the probers. Hover your mouse over the first thick line on the D1 channel 1 and use left control and the mouse wheel to zoom in again. You should be able to see the entire signal transfer. So we're going to go to D1 channel 1, the first thick line, and we're gonna, oh hello, okay, something's happening. What is very interesting from the screen is that you can see how the analog voltage data corresponds to the digital signal that is seen. So you can see the analog data and the digital data. Looking at the A1 channel versus the D1 channel 1, you can see that there are slight breaks in the analog data that have been corrected in the digital channel. Now that we can see the digital signal data, we can look to use the logic analyzer to read the contents of the data. Click on the analyzer tab to the right. So we're going to come in here and we're going to click on the analyzer tab. Since we know the protocol is USART, let's look to configure the async serial analyzer for both channel 1 and 0. Let's configure channel 1's analyzer first. If we were true hardware reverse engineers, which we're not, we would first have to figure out the rate at which the data is being transmitted. I assume that's the baud rate, as well as the specific configurations such as the parity bits and frames. However, to keep this simple, Forensic Elf has already discovered this for you. Alter your configuration to match the following and click Save. Okay, so all I'm going to do here is I'm going to click on Async Serial and hope for the best, because this produces a box where we need to configure stuff. So we're going to select the channel of 1 as per the documentation, and we're going to select the bit rate of 4800. We're going to keep it as 8 bits per transfer standard with 1 stop bit, no parity bit, least significant bit sent first, non-inverted standard, normal. We're going to keep these 2 boxes ticked and we're going to click Save. Once saved, we can see the data is being analysed. Click the little terminal icon and we can actually read the data being transmitted. So I guess we come into here, click on the terminal icon which is there. Let's make this a little bit bigger to see. Okay, so we can see we have some data and it says ACK and reboot. We can see the initialization sequence of the serial line and then the 3 lines of data being sent. ACK reboot CMD X1958837 blah 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 9600. This doesn't yet mean anything since we are only seeing one side of the data. In order to see the other messages, we need to add another analyzer to channel 0. Click the plus icon next to analyzers and add another async serial analyzer with the same configuration except for channel 0. So I'm going to come in here and there's a little plus symbol right there and I'm going to choose async serial. I'm going to choose channel 0, I think it said. Yeah, channel 0 with the same settings that we used before. So we're going to use 4800 bit rate, 8 bits per second, 1 stop byte non-parity. Yeah, it saved it all for us, so I'm going to click Save. And then it says, once added, click the trash icon in the bottom right hand to remove all terminal data. Once done, click on the 3 dots next to each analyzer and select Restart on both of them. Your terminal should now look something something similar to this. So we head into this window and we hover down here. The trash icon isn't visible until you hover, and then we click and clear terminal. Then we come up and we go to the 3 dots next to each one and we click restart, and then I assume we click restart again, and we have a message. So we have the ACK reboot. Hello command, please send security string, security setting accepted, please specify new baud rate of 96,000 accepted. And that looks like we got some hex. Now we are starting to piece together the information. It seems like the microprocessor is establishing a session with the ESP32 device to allow communication to the control server. We can now see the full discussion between the two devices. The processor asks the ESP32 to reboot its connection to the control server. The ESP32 is happy to oblige but requests a security code to be sent to allow the communication to the control server. Once the security code has been transmitted, the ESP32 allows the microprocessor to negotiate a new baud rate to communicate between the two devices. Interestingly, once the new baud rate is accepted, we cannot read the rest of the output. However, since we intercepted the baud rate, we can simply edit our channel 0 analyzer to the new baud rate to read the rest of the communication that was sent. Go and make this change to get your flag. So we have our 2 channels and we know we now need to change it to 9600. So I'm hoping we can just click on one of these and click edit, and then change this to 9600 and click save. And then maybe we do the same for the other one, or do we already have the flag? Let's change the other one as well to 9600. Click save. Then let's trash the output like we did before and then click restart on both, and maybe we get something. Okay, we've actually got something. So we see the new baud rate has been accepted and we're sending a new administrator code, which is THM. Hacking hardware is fun. We have our flag. So I think we can answer all the questions now. What device can be used to probe signals being sent on electrical wires between devices? Well, we know that from the room is a logic analyzer. Fantastic. Is USART faster than SPI for communications? We know that's a nay due to the different wires. USART communication uses fewer wires than SPA, yay or nay? I'm going to say that's a yay. USART is faster than I2C for communication, yay or nay? I'm going to say that's a nay. I2C uses more wires than SPI for communication, yay or nay? I believe that's yay. I believe that's nay actually. SPI is faster than I2C for communication, yay or nay? I believe that's yay. What is the maximum number of devices that can be connected on a single pair of I2C lines? I believe that was 1008, if memory serves correctly. What is the new baud rate that is negotiated between the microprocessor and the ESP32 chip? Well, that was 9600. And then finally, what is the flag that is transmitted once the new baud rate was accepted? Well, we've got that right there. THM hardware. Hacking hardware is fun. So we're just going to go THM hacking.hardware. Hopefully that's right. Whoop whoop. Looking for a new challenge? Try our recent threats module. Whoa, okay, so we are done. This was a really interesting room. I learned a lot. I'm not sure how much of it I retained, but that's always the case with all new protocols that we learn, I suppose. It seems that all these protocols mimic some other type of network protocol in a certain respect, in the way that they do error checking. And anyway, I'm knackered after that. That was hard work. John Hammond has done an excellent video on this, more knowledgeable than I am. Go watch that as well. He probably explains it a lot better than I do. But that is all I have for you today. I hope it helped you get through the room. If it did, like and subscribe. And I will see you next time. Kind regards.